All right, so we're going to start this Unit 2 project. And first of all, I want to tell you that I modified the name of it. It was originally called KE equals PE. That was the name that the district gave to it. And what do those things stand for? What does KE stand for?
Kinetic energy.
Kinetic energy. What's PE stand for?
Potential.
Potential energy. And what's ME stand for? Mechanical energy. Okay? So originally it was called kinetic energy equals potential energy, right? And I thought that was a little strange because basically now I've put potential energy into the ball, right? How do I turn it to kinetic? I let go, right? And it becomes kinetic. Is it true that you can turn potential into kinetic and then back and forth? Yeah, that's true. But I also like adding this little detail that mechanical energy equals the sum of kinetic plus potential. Okay? I thought that was kind of an important detail to include, and that's why I changed the name of it here. Now, like the other project that we looked at, there's kind of a little introductory couple of pages that are not really part of the project, but it's just interesting stuff about science and the world around us. So if you look in the background here, what does this photo look like to you?
Space.
Yeah, and that is a particular location in space. It's called the Orion Nebula. And so a nebula is a cloud of gas and dust in space. It's huge. It's way bigger than the solar system because this is where stars are born. And can you see these really bright young stars right here? These are the ones that were just born. And so if you have a telescope, you can see the Orion Nebula. And it's kind of cool looking if you ever get a chance to do that. But this photo has more than a telescope view. You see these kind of swirling lines going across there? Those are lines of magnetic force. They're the field of magnetism, the magnetic field in the Orion Nebula. And remember, each little star in here is the size of the sun. So this stuff is huge, huh? And it's kind of weird for me to say, well, this is where stars were just born, because it takes like 100,000 years for the light to get to us from Orion, which means they're actually 100,000 years old. And do they look like this anymore? No, because it takes so long for light to travel. So the Orion Nebula is named for the hunter Orion. And if we look at Orion, he's got a couple of bright stars that make up his feet. Oh, by the way, this is on the next page, too. Let's go to page 2. Did you put your name up here in the top?
Yes.
Let's go to page 2. And it shows you a star chart, a map of the stars to help find Orion, which actually here he's upside down. So I'm going to draw him right side up here. Here's his feet. A couple of really bright stars that make up Orion's feet. A couple of really bright stars make up his shoulders. His head is not so bright. I don't mean any offense to his intelligence by that, by the way. And then probably the most famous part of Orion is his belt. Have you heard of Orion's belt? It's these 3 quite bright stars in a line close to each other. Pretty cool to look at, but that's just his belt, right? And so if we connect these together in our mind, we kind of have a shape like this, huh? Yeah?
Yes.
Now Orion is the hunter. So there's also a set of stars. They're not in a straight line. They make an arc, kind of like a bow. So this is his bow over here, like his bow and arrow. There's his belt. Here's his feet. And then we can, in our minds, imagine that he's standing there with a bow and arrow, right? Ready to hunt something. But for us, what we're really interested in is that Orion also has, hanging from his belt, he has a sword. So he's got this sword here, and if you point your telescope at the middle of the sword, that is the nebula in Orion, the Orion Nebula. So that's where that photo on page 1 was looking at. But you wouldn't see those lines streaking through it. That was added in there because they were able to measure the magnetic field. Personally, I think it kind of looks better without them. It's a beautiful, kind of a glowing cloud in space. It's really cool. Yes, sir?
How come there it says the fuzzy spot is belt?
Because I'm giving you a little more detail than that. It's not in the belt, it's actually in the sword. Yeah. So, right, the other thing about Orion is it's known as a winter constellation because it's easiest to see in the winter. In the summer, it's of course still up in the sky, but it's up during the daytime. So would we see it? No, the sun's too bright. You can't really see the stars. They're there though, aren't they? So we see Orion best in the winter, but yesterday morning when I got up, I looked outside about 6 o'clock and I could see him. So, you know how the sun rises in the east and sets in the west, right? Same thing with all the stars. So Orion is probably rising in the east around 10 p.m. So if you were like down at the beach and you looked above the hills to the left, around that time you should see Orion coming up. And then at 6 in the morning he was ready to set behind the western horizon, huh? Okay? So that's just a little background about some interesting stuff about astronomy. But let's get started on the actual lab, okay? So go to page 3. And you can see once again, here's the title of the whole thing, Mechanical Energy equals Potential plus Kinetic, right? All right. Andres, will you read the next line for us? Right there.
Page 3.
Page 3, yeah.
Chemical energy equals potential energy plus kinetic energy.
Yeah, and we talked about that a moment ago, huh?
Yeah.
Right? Okay, who's going to read next? Andres, choose between these 5 people here. Okay, Sam, what's the next line say?
Energy is conserved, never lost, never gained, just changed.
Okay, so this is the law of conservation of energy, isn't it? Which most people say that they describe the law as saying energy cannot be created or destroyed, but it can be converted from one form to another. Is that what this just says in different words, though?
Yes.
We never lose it, we never gain it, can't be created, can't be destroyed, right? But we can change it. So do you remember we did some stuff with the basketball? So for instance, if I drop it from up here, right at this very moment, before I let go,
Potential.
it's all potential energy, isn't it? And then as it's falling halfway down, what is it?
Kinetic.
Kinetic and
Is it?
potential.
It's kinetic and potential. And if it's exactly at the halfway point, it would be 50-50, right? Then at the moment it hits the table,
Kinetic.
it's all kinetic, huh? And I mean, just imagine if you were lying there on the table and I dropped it on your belly, you would know that energy got there, huh? Right? And so we can do a diagram to show this. And here's where it's at the top. Here's where it's halfway down. And here's the very moment that it hits the table. Right? Now, supposedly I drew those squares. I didn't do a very good job, but what if they were all exactly the same size? Would that show conservation of energy?
Yes.
Right? We have the same amount of energy all the time. When you conserve something, you keep it, you save it, you have the same amount. Right? So, by drawing these squares the same size, I'm showing that the total amount of energy is always the same, and that total, of course, is the mechanical energy. Right? The mechanical is always the same. But the potential and kinetic are changing, aren't they? So if this is the top before I dropped the basketball, what percent of energy was potential, what percent was kinetic? I'm holding the ball up here, getting ready to let go of it. What percent is potential right now? What percent is kinetic?
100%.
Sorry? Again?
All of it.
All of it is what?
Potential.
Potential, yeah. So here, it's 100% potential. And 0% kinetic. And I could do this where a blank square means potential energy and a striped square means kinetic energy, huh? Right? Now at the moment that it's halfway, it's falling, it's in the process of falling, what are my percentages?
50-50.
They're 50-50, right? So right here it would be 50% potential, 50% kinetic, and my diagram would now look like this, wouldn't it?
Yes.
Yeah? The size of the square is still the same though, huh? Because energy is conserved. What about at the very moment it hits the table?
All kinetic.
At that moment, it's 100% kinetic and no potential, huh? 0% potential, 100% kinetic, and it would look like this in our diagram, huh? So are we showing the conservation of energy here? Is this a diagram showing this? Yeah. It's showing that it's conserved because it's always the same amount. So it's not being created or destroyed, but it's changing, isn't it? Right? That's conservation of energy. Who read that one? Sam, who's next?
D-line.
Okay, Dylan, what do you got here?
How can I use models
Uh-huh.
to help me understand how energy is transferred and transformed?
Right. How can I use models to help me understand how energy is transferred and transformed? So we're going to be making some models to try to understand these energy transfers. Who's next, Dylan?
Who's next?
Yeah, who's going to read?
Oh, Josh.
Well, Josh is not included. It's one of these two ladies, actually. Okay, kids, so they read the box.
Okay. No, model. Model could be physical object like a model car or a globe. It could also be a diagram, a picture, a graph, a math equation, or even an idea, which we would call a mental model.
Nicely done. So look around the room. Where do you see a model? A physical model. Okay, I suppose we could consider this board that's got these measurements on it to be a model of distance, huh? Right? What are you pointing at, Kaylee? The globe. Isn't that a model of the world?
Yeah.
Right? What about this diagram right here? Is this a model of the amount of energy and how it's changing? Yeah. What about my diagram of Orion? Was that a model of what the universe is like? Right? And not only that, I drew it from memory, huh? Since I drew it from memory, does that tell you that I have a mental model of Orion? And do you have a mental model of your house? And a mental model of the school? Right? So we want to improve our mental models of energy transfer during this unit. Does that make sense? That's what we're driving at. Okay? All right, so now we're ready to do the lab. And I'd like you to arrange yourselves so that you can see this board here. And you had a question? Could it be quick?
Yeah, I was going to ask you,
Yes. Okay, so are you guys all on page 3? Yeah, we've been reading that together, right? So notice that we've got a list of things to do, numbered list of things to do. For number 1, we don't have to write anything though. It's just telling us what to do. So I'm going to take this basketball and I'm going to drop it from this 1 meter mark. the bottom is going to be lined up with 1 meter. And then I need a couple people that are close to film this with their cameras in slow motion, because what we want to do is measure how far it bounces back up.
I don't have a good
And the best way to do that is with your phone.
You have a good phone?
Yeah,
You do.
I can do it.
Great.
My phone is terrible.
Now, you need to be able to see these lines in the background. So I don't know if it's going to work very well from where you're sitting. You're going to film it too, Andres? Great. You're going to film it too? Perfect. So we'll have 3 different measurements to look at. So if you, probably be best to do it in slow motion, right? So you got to tell me when the bottom of the ball is lined up with that 100 centimeter mark. Okay, because that's where we're dropping it from. That's where we're measuring. Tell me when it's in line.
With the 110.
With the bottom of it is at the 100 mark. Do I need to go higher or lower?
Good.
Good.
Right
That's
there.
good?
Right
Are you ready to film?
Yes.
3. Well, start filming. 3, 2, 1. Okay, so we want to see how high it bounced the bottom of the ball. Okay?
there. Behind the bottom.
So zoom in if you can, and you're going to have to like step one step at a time through the film till you get to the maximum point where it bounced up, right? The highest point where it bounced up, we want to look at the bottom of the ball and measure that against the background. Try to be precise as much as possible. Was the bottom of it at 70, past 70, or not quite 70? Okay. You agree?
Yeah.
Okay.
Me too.
Yeah, like 60.
Okay. So for number 2, you're going to record, you can type it over here, that it bounced 69
That was in
cm.
a fast motion.
Bounced 69 centimeters, right? Okay, we're going to do it again, but we're going to do it with a tennis ball. And what I want you to do, it doesn't say it on number 3, but I do want you to write in next to number 3 a prediction. So I want you to predict for number 3, do you think the tennis ball will bounce more, bounce less, or the same as the basketball? What's your prediction?
We put 69 centimeters for number 2.
Yes. Number 2 would be 60. Number 1, you don't do anything.
Oh.
Number 2, 69 centimeters. Number 3, predict if you think the tennis ball will bounce more, less, or the same. Am I going to lower your grade if you don't predict correctly?
No.
No. Am I going to give you bonus points if you do predict correctly? No. Am I going to take points away if you don't predict?
Yes.
Yes. That's the only way you can lose points is by leaving it blank. So number 3, make your prediction, and then let's get those phones ready to film again.
Is that 69 centimeters?
Yeah, that was 69 centimeters for number 2.
So for number 3, we'll put the
Number 3, just predict if you think the tennis ball is going to bounce more, or if it's going to bounce less, or if you think it's going to bounce the same amount. Make a prediction. All right. And let's get those phones ready to go. And once again, you got to tell me when the bottom of the tennis ball is lined up with the 100 centimeter mark. Do I need to go higher or lower, or am I good?
The 100? Lower.
This one, yeah, the 100 has to,
Yeah.
the bottom of it should be there.
A little
A
bit
little
more.
higher.
Higher?
Yeah, that's good.
Yeah.
Good?
Yeah.
Filming?
Oh wait.
And 3, 2, 1. Make sure you measure the first bounce, the bottom of the ball, right?
Oh. It bounced less. Did you guys get less?
Yeah.
Yeah, I got it.
You do more?
I put more.
Gonzalez.
Yeah, I put like 70.
So how much, what's your measurement?
Like 65?
What's the highest? Okay.
Yeah, about 60.
The first bounce, right?
Like, yeah, 63, 64.
Well, it looked like it just barely went past 60 to me. Can you pause it at that high point?
I have it. It's at like 63.
Okay. Okay. Yeah, does it matter what the exact number was for our purposes here? Not right now, it doesn't really matter. So if you have 61, that's what it looked like to me on yours. That's fine. If you have 63 on yours, that's okay too. It's probably because you took it from different angles. We have a little difference, huh? All right. Number 3. Actually, it's number 5, but it's our third test, isn't it? So check this out. For number 5, what we're going to do is I'm going to drop them together at the same time with one stacked on top of the other, like this. Get it? Okay? So for number 5, what I want you to do is start by making a prediction how high you think they're going to bounce.
No, that tennis ball is going to
And yeah, it's not a rubber ball, it's going to be the tennis ball. How high do you think they're going to bounce?
The tennis ball is going to go.
When I drop them together at the same time.
The tennis ball is on top.
The tennis ball is on top of the basketball, and I drop them together.
Same prediction of both.
Yeah, you're going to predict each one. How high is the basketball going to go? How high is the tennis ball going to go? And then jump to page 4. Before we do it, we're going to make a model of our prediction. So when you look at this diagram on page 4, what I want you to notice first of all is that it has a left and a right side. So on the left side is where we're going to make a prediction. On the right side is where we're going to do the actual. So for example, on the left side, what you can do is you can make a circle. So you make a circle the size of the basketball, and you make another circle the size of the tennis ball, and you drag that to where you're predicting that it's going to bounce. Right? And then I'd like you to also make an arrow. Now I changed the properties on this arrow so it was bigger and darker than the automatic one. And show the ball bouncing up. So the dotted line balls are the ones where we're bouncing from. And so you're going to make your prediction there. So you made both a basketball and a tennis ball on the diagram, right? And you put an arrow in there to show them bouncing up? Yeah, this is the bounce, and it's going to go up from there.
ball is gonna hit the ceiling.
Oh!
Either that or it's gonna get launched right at me. It could bounce weird, you know. Oh wait, you're dropping it at the same exact time, correct?
Yeah.
Oh wait, never mind.
Maybe.
So I'm going to drop them like this, right? Simultaneously.
Oh, I thought.
Yeah?
We should do a test run.
Well, the test run is the actual data collection, right? I want you to predict before the test run. And when you're ready, we need to get those cameras set up and ready to film again. Right. Okay. So once again, you got to tell me if I have to move this up or down, right? Tell me if I'm going to raise it or lower it. Where do I need
A
to
little
go?
bit down.
Down?
That's good. A little bit up.
Up?
Yep. A little bit down.
Down?
Yep.
Right there.
Are we ready? 3, 2, 1.
Yeah,
I knew it.
I knew it.
Let's try that again. And it went off at a weird angle, huh? Thank you, sir.
My mom really called me Anson.
So if I do it again, I'm not going to worry about it being perfect. We got a measurement of the basketball, though, didn't we?
Yeah.
So that's good.
I told you it was gonna hit the ceiling.
Let's do another one. Ideally, it's going to go straight up, right? That's what I want to have happen. It's a little tricky. That's better.
Oh, damn, I forgot.
Okay,
You forgot the
so
patent book.
what I want you to do is go to the basketball and find out how much that one bounced, first of all.
About 35.
And then that is going to be recorded. If we go back to page 3,
Number 6.
yeah, for number 6, you're going to write down how far it actually bounced. The bottom of the basketball.
Mr. Fairley,
Yeah.
my computer can't download this on the school Wi-Fi, so I'm just taking pictures of it.
Wow. Okay.
It's very, yeah. I haven't actually watched it yet.
Okay, let's think about this, you guys. When these were falling together, right? They're falling together, and then they hit the ground, correct? What was it that shot the tennis ball up to the ceiling?
The kinetic energy.
How did that tennis ball gain that energy? Because here, when I dropped it by itself, it didn't gain anything, did it? It only lost. So where did it get energy from? It got energy from the basketball, right? Meanwhile, what happened to the basketball? Did it bounce as high as before? Why not?
Did transfer the energy into the tennis ball.
It gave up some of the energy that it had and sent it to the tennis ball. Now the tennis ball got a ton of energy from the basketball and hit the ceiling, right? And I think that's because the basketball's heavier than the tennis ball. So when it's falling, it has more energy than the tennis ball does. And then it transferred all of that to the tennis ball. Well, not all of it, like half of its energy went to the tennis ball, huh? And because it was smaller, it went flying up to the ceiling. Does that make sense? So we also need to add to the diagram on page 4, right? You're already doing that? So you want to write down the numbers on this page for question 6 And then you want to add to the diagram on page 4.
Just about the basketball?
No, both of them. Well, that's right. For the tennis ball, what do we want to do? For now, we're just going to estimate. So what I'm going to do is just measure the ceiling.
So like on page 3, right?
Yeah, I forgot about the tennis ball. Thanks for the reminder, Andres. So this is 1 meter, right? Or 100 centimeters. It's the same. And that makes 100, 200. So we hit the ceiling before 300, huh?
Yeah.
But we know the tennis ball wanted to go farther than that, huh? So for now, let's just call it about 300 centimeters for the tennis ball. So then we're going to go to page 4, and we're going to make another basketball and another tennis ball. Oh, beware of one thing though. The 0 meter mark is not this heavy black line at the bottom where they drew these bouncing. And I can tell because I counted the boxes here. The 0 meter mark is actually right here. This is 0. And the reason I can tell because that's 20, 40, 60, 80, 100, huh?
Oh, yeah.
Right? So this is actually 0. So you want to be careful with that. And then I'm going to drag my basketball. How much did you guys decide it bounced?
35. I got 35.
You got 35? So there's 0, there's 20, there's 40. Well, it didn't go 40, did it? So I better lower it about to there, huh? Right? And then I'm going to take an arrow. I'm just going to copy and paste the one that I made earlier. And I'm going to put that arrow underneath it.
Yeah.
For the first drop for the basketball.
For test 2,
For the first one.
69. The first one?
No, like when we dropped it with the tennis ball on top.
35.
And then the tennis ball went flying off the top of that because it gained some energy from the basketball. And we're going to put the tennis ball somewhere around 3 meters, right?
Wait, did we drop it 4 times? With the
No.
tennis ball?
No, you're looking at the chart, aren't you? What we're going to do is next class, we're going to come fill in that chart. Because this room the ceiling wasn't high enough to actually measure the tennis ball, was it? So we're going to go into the gym and we're going to do this again 3 or 4 times and measure the average. Does that make sense?
So we can only like fill in the first 3.
I don't want you to even do the first 3. All we're going to do is the diagram right now. And then just don't fill in the chart at all. Instead, just write the height that we got for number 6. Just do it over here. Okay? Just write down basketball 35 centimeters and then tennis ball 300 centimeters or so. Okay? And then next class, we'll come back and we'll do this all over again in the gym where we can measure it better. Does that make sense? Yeah.
I'm a little bit confused.
Okay.
Would we write like
This was your prediction.
Oh.
That's where you, okay, yeah, you were supposed to predict beforehand, right, what was going to happen. And you drew a prediction, didn't you? Okay, good. So what did you predict? Was this your prediction or the actual? Okay, so you predicted that the basketball was going to go 115, it looks like, right? And that the tennis ball was going to go 3 meters or 300.
Yes.
Yeah. Okay? So just put those numbers as your prediction back at number 5. Okay, and so that's all we have for the project today. Like I said, we'll come back next class and we'll do these multiple times in the gym where we have a higher ceiling. And I'm going to make one of these on some on a big roll of paper that'll be like 5 meters high that we can measure. We'll hang that on the wall, and then we'll do it in there. Sound good?
Yeah.
Okay.